Shah. I am here to discuss one of the emerging technologies of semiconductor, which is organic field effect transistors. The outline of this topic are how to design OFET, how to prepare OFET, transfer characteristic of OFET, carrier transport, advantages and application of organic field effect transistors. Organic field effect transistor is a field effect transistor using an organic semiconductor in its channel. They can be prepared by vacuum evaporation of small molecules or by solution casting of polymers or small molecules or by mechanical transfer of built single crystalline organic layers onto a substrate. They are fabricated with various device geometries. Out of them, the most commonly used is bottom gate with top drain and source electrodes, as it is similar to thin film silicon transistor using silicon oxide as gate dielectric. Organic polymers such as polymethyl methacrylate can also be used as a dielectric. OFETs adopts the architecture of the film silicon transistor. With the development of conducting polymers, the semiconducting properties of small conjugated molecules have been recognized. The performance of OFET has improved significantly in terms of on and off current ratio and can compete with the performance of thin film silicon transistors. One main attraction of this technology is that all the layers of an OFET can be deposited and patterned at the room temperature by combining low-cost solution processing and direct write printing. Now let's discuss how to prepare the OFET devices. Thermally oxidized silicon is traditional substrate for OFETs, where silicon dioxide serves as a gate insulator. The active field effect transistor layer is usually deposited on a substrate by thermal evaporation or coating from a organic solution or electrostatic illumination. Thermal evaporation and coating uh, techniques result in polycrystalline active layers as they are easier to produce, but they result in relatively poor transistor performance. The schematic of OFET is shown in the figure. Electrostatic lamination technique is based on manual piling of thin layer of a single organic crystal, so it results in a superior single crystalline active layer, but it is more tedious. The thickness of gate oxide and the active layer is below 1 micrometer. The transfer characteristic of OFET is shown in the figure. The charge in the channel is modulated by adjusting gate voltages, so the device behaves as a variable resistance. When voltage is applied between source and gate, majority carriers accumulate at the insulator semiconductor interface, which leads to the formation of a conduction channel between source and drain. Now let's see how carrier transport take place in OFETs. Carrier transport in OFET is specific for two-dimensional carrier propagation through a device. Various experimental techniques such as transit time of injected carriers, time of flight to determine the carrier mobility, organic monolayer experiment for probing orientation dipolar changes, optical time resolved, second harmonic generation, etc. for the studies. Carriers propagate through polycrystalline OFETs in a diffusion-like manner. They move through a conduction band in the best single crystalline OFETs. The most important parameter of OFET carrier transport is carrier mobility. The evolution of carrier mobility over years of OFET research is shown in the graph for polycrystalline and single crystalline OFETs. The graph reveals that the mobility in polycrystalline OFETs is comparable to that of amorphous silicon, whereas mobility in organic semiconductor like ruprene-based OFET approaches that of the base polysilicon devices. There are many advantages of organic field effect transistors, which are as follows. It is less complex and lower cost fabrication. It has mechanical flexibility as it is compatible with plastic substrate, as plastic substances are foldable and lightweight. Moreover, it has strong optical absorption and efficient emission, which can be used in organic LEDs. Organic field effect transistors can be used in various applications. Some of them are as follow. It can be used in flexible, low-weight, large area displays such as organic LEDs and the thin-film silicon transistors. It can be used also in optical recording, which is based on optical absorption. In circuits printed on papers and electronic papers, organic field effect transistors can be used. It is also used in ultra low cost, low performance applications such as smart cards, and also used in low heat dissipation circuits. Organic field effect transistor is compatible with huge varieties of substrate. It is also reliable readouts according to product requirements. It can yield enabling profitable manufacturing. It gives a proof of concept for simple and cheap manufacturing methods. It also brings down the supply voltage to 1 volt, which is also realization. Thus, organic electronics is ready to meet the requirements for product realization. Thank you.